Thank you. All right, so thanks for coming to today's seminar. Nice to see a good crowd of people here in the summertime in Ithaca. Our visitor is Dr. Zixin Huang, who's here in Ithaca, coming from Rochester. She seems to enjoy Ithaca a lot more than Rochester, and after this, she'll go to Denver. So we're pleased to have her here, not only for the seminar, but also having some interesting research discussions. She's an expert in a variety of topics, including quantum metrology, quantum imaging, which you'll tell us about today. She's done work with like bosonic Gaussian states and channels, applying ideas of hypothesis testing and state discrimination to problems of physical interest, like exoplanet detection. Yeah, so a variety of things. You did your PhD at University of Sydney, graduated 2017, 18, all right. And did her postdoctoral work at University of Sheffield with Peter Koch. And then now you're at Macquarie University as a Sydney Quantum Academy Fellow. And we've been working together and having a variety of discussions for some time. And in January, she was the lead organizer for a conference in memory of our late colleague, Professor John Dowling from Louisiana State University. And so that was a very nice conference that you organized, and I was very happy about. Okay, so and today you'll tell us about this interesting work. I guess people are welcome to give questions, to ask questions.
Yes.
Okay, just a second.
Yeah, so wow, thanks everyone for turning up, and then thank you, Mark, for the invitation to be here. I'm very happy to be here. And yeah, I'm happy to take questions as we go. So, and I'm thinking, so how many of you are undergrads? PhD students? Post PhD researchers? Okay, great. Thank you. Yeah, so yeah, my name is Zixin. I am a postdoc fellow currently working at Macquarie. So I'll be telling you about the work that I've been doing at Sheffield and also at Macquarie. So yeah, so this is a multinational collaboration, however many authors, about 6 nationalities. So yeah, I'll be telling you about quantum imaging techniques mainly applied to astronomy, but anything that I say here will apply to microscopy because we're working with light, and electromagnetism seems to be universal. Okay, so here's the roadmap for where we're headed. So the motivation is that we want to surpass Rayleigh's criterion. And then I'll go into quantum hypothesis testing for exoplanets. I'll tell you a bit more about an experiment that we did in collaboration with Harry Watt University. And then I'll tell you about how to enlarge the baseline of current imaging systems. So I lied in the abstract. I think I said I'll do the large baseline stuff first, but I decided to do it in reverse. Okay, so from Astronomy 101, you know that if we try to take an image of a point source in a distance, then your picture on the image screen is not a point source due to the fact that your imaging aperture is finite. So if you have a circular aperture, then the point source would have a finite spread characterized by point function. And here we have a sink due to the fact that the aperture is circular. And traditionally, astronomers say that the minimal resolvable angular separation between 2 sources, theta is approximately lambda, the wavelength, divided by d, which is the aperture, the diameter of your lens. So here, they say that 2 sources are resolved if the trough of the point spread function of one is further away than the peak of the other. So here you have resolved, just resolved, and these are barely resolved as they merge together. So we want to use as small a wavelength as possible and a large wavelength, diameter as possible. But okay, that comes up with its own problems. But for realistically, the smallest wavelength we can use is optical because ultraviolet gets absorbed by the atmosphere. Yeah, so we want to somehow surpass this criterion or curse, as Manke-Zhang has termed it. Now, if we are tasked with estimating the separation between these two sources, so here we have θ2 is our parameter, we can probably imagine that this task becomes more difficult as the 2 point sources become closer and closer together. So, and what does that mean when we say the task becomes increasingly difficult? So whenever we are estimating something, we want to dig into the quantum metrology toolbox. So the Cramer-Round bound states that if you have a parameter phi that you're interested in estimating, so this is a variance of the parameter, it would be lower bounded by 1 divided by nu, the number of copies of the quantum state you have. So in our case, this will be the number of photons that you receive, multiplied by the Fisher information of the state. Now, the Fisher information is defined by this quantity over here. So if you have a set of measurement outcomes I occurring with probability pi of phi, then the Fisher information is given by the derivative of the log of pi of phi squared weighted by the probability of occurring. I mean, you can replace this summation by an integral if you have a continuous distribution. And so basically what this means is that if your probability distribution changes very rapidly with the parameter, then you get a high Fisher information and vice versa. So this is the information content of your distribution. So you want a large Fisher information if you want high accuracy. So the quantum analog, if in place of a measurement distribution, you have a quantum state, then you replace P with your density matrix, and you can derive the quantum analog, which is a quantum Fisher information. So the quantum Fisher information is only dependent on the state, and it's effectively a maximization over the Fisher information over all possible measurements. So large quantum and Fisher information, that's good. Small, that's bad. Okay, so let's go back to our estimation problem. So in our model here, we have two sources which are incoherent with respect to one another. So our density matrix looks approximately like this, where half the time you have the photon coming from one of the sources, and other half the time is coming from the other. This is the probability distribution on the image stream. And you can go ahead and calculate the Fisher information for estimating θ2, the parameter. And the Fisher information drops to 0 as the separation becomes close to 0, which is once again very intuitive, because as the two merge, this becomes a blob, and it becomes very hard to distinguish that there are two. But if you calculate the quantum Fisher information based on this state, you can see that it actually stays constant all the way up to 0 separation. And at the time, I think this paper came out 7 years ago now, and that was that dropped the bombshell on the quantum community because, well, super resolution, that was great. But you probably won't believe me until I show you a physical measurement that can saturate this quantum Fisher information, QFI. And it looks something like this. So you take the centroid of your two sources and you put it into something that can spatially demultiplex. So here we're using the eigenbases, which are Hermite-Gaussian modes. And they look approximately like this on the image screen. So this is the fundamental mode, which is Gaussian. This is the first order mode, which has a dip in the middle, and higher order modes, they start getting more and more dips. So what you do is that you put the center of your binary system into this spatial mode sorter. Here we're drawing it as a waveguide because Hemigaussian modes are very natural modes for a waveguide. And then because these modes are orthogonal, so in principle, we can sort this out. And then so you sort out these modes somehow, and then you do photon counting. And this measurement saturates this bound. So the idea is that if the two modes are very, very close, then mostly they overlap with the fundamental mode. And so most of the light goes into the fundamental mode. And if they are getting spatially separated, then they start exciting the higher order modes. And this particular measurement is very sensitive to displacement, the spatial displacement of the sources. Right, so yeah, ever since then, the two-source problem has been studied to death. We applied it to LiDAR, multi-dimensions. We extended to an arbitrary number of sources.
May I ask the two-wave function, they are coherent or incoherent? Like they're in a pure state or they're in a
so this spatial distribution that is coherent because it's one mode that just happens to be Gaussian shape. But these two sources are incoherent.
If they're incoherent, they can still be projected onto the series of modes, fundamental, second mode.
That's right.
So okay.
Yeah. So actually, this method was precisely designed for incoherent sources. If there is coherence between the two emitters, then you can do other stuff with it. So yeah.
Thank you.
Yeah. So until I remind you, there is no entanglement and no squeezing involved in this talk. Yes.
I have a question. Can you go to the next slide? Maybe you said this already. There's the spatial demultiplexer, and then these are photon number measurements. What kind of measurements are those?
They are photon counters.
Photon counters.
But because we're considering astronomical sources, then at most we get one photon at a time.
Okay.
Because
you just need like on-off for each.
Basically, because it's very rare that you get more than one photon at a time, but we can take that into account.
Right.
Yeah. And because the theta is thermal, the photons are independent anyway.
A very basic question. I think you said, but I missed it. I'm trying to get some intuition about what really makes this possible. So what is really the fundamental thing that makes super resolution possible here?
Okay, so I guess we are benchmarking against direct imaging, and that is not optimal. So this is optimal because you're basically measuring. So you have a point spread function that's coming from the imaging system, and you're projecting onto the eigenbasis of.
I can do that classically, right?
You can do that. Everything's classical here.
So everything is classical so
yes,
far.
Correct. But it did take a quantum information theorist to find it.
But if it is classical.
Yeah.
I have to read the paper, but
So pressing on Francesco's question, so if the two sources are not single photon emitters, will this break down?
Not single photon emitters.
Right. If they can emit billions of photons simultaneously, which are spontaneous emission, will this break down?
Thermal sources.
Thermal sources.
They are considering thermal sources.
That's thermal sources. Okay, so they're not single photon emitters.
Yeah. So it's mathematically much easier to consider receiving like one photon at a time per time bin, but we can do thermal. I think it just like as your mean photon number increases per photon, the quantum visual information decreases, but it still works.
So before this paper, it was thought to be impossible to distinguish two below the Rayleigh criterion.
Well, I'm not sure we thought it was impossible. People have all different sort of tricks that they can do. For example, for microscopy, you would do like, suppress, you can do source engineering.
Classically, usually, so if you want to go beyond the diffraction limit, you can either do what you were suggesting, so that's based on nonlinear properties, right? Or you can go in the near field.
Right.
In the far field, I mean, sure, even if you're able to separate all of the modes, and they don't have to be these waveguide modes, this could be just plane wave modes.
Yes, that's right.
Sources.
Yes.
If I were able to count all of those photons, well,
The trick is to maximally measure the information that's in the state. So I think direct imaging was just not optimal. Yeah.
I have to separate into the modes, and then when I count photons at that level, I can do better than a direct imaging procedure.
Cool. Yeah, so we have all these nice tools that we've developed, including that one. And we thought, what else can we do what else can we do with it? And the intuition was, if these methods are very good at measuring the separation between things which are very close, then maybe it'll also be very good for detecting sources which are very close. And one very natural thing that we did was looking at whether it would be useful for detecting secondary sources. So we applied it to exoplanet detection, and we found this nice, surprising result. So if we're talking about detection, then the tool we want to use would be a quantum state discrimination problems. Oh, sorry, the tools we want to use would be from quantum state discrimination. So here we have two hypotheses associated with two density matrices or measurement probabilities. Oh, sorry, there's a typo there. So classically, if we are looking at direct imaging again, then we have two photon intensity distributions on the image screen. So for the null hypothesis, we have a PSF coming from a single star. For hypothesis one, the alternative hypothesis, you have a parent star that's bright, and next to it, maybe embedded in its intensity tail, a planet that could be much dimmer. So here we're preserving the total photon number just because you may not know the mean photon number of the star or the planet exactly. So we're saying, let's receive a set number of photons and see what we can get with it per photon. So epsilon is the relative intensity of the planet, and they're separated by some angular separation S. So classically, you have P0 and P1, and quantumly, you have ρ0 and ρ1. So there are two fundamental results for quantum state discrimination. If you want to weigh your false positives and negatives equally, then you would look at the quantum Chernow bound. But for us, we have a slightly different problem because exoplanets are rare and habitable exoplanets are even rarer, and you probably don't want to miss an exoplanet in case it's there. And for that one, the relevant quantity of interest would be the quantum relative entropy. So it's given by this expression over here. So how many people have not seen it before? Okay. Yeah. So the theorem states that if I'm happy to accept a certain threshold for false negative, so for example, if we think mistaken that there is a planet there, then you just look closer. That's a false alarm. We set that to constant, then the probability that you missed a planet will be given by this expression over here. So this is a probability of error. N is the number of photons you get. E is the relative, I should have fixed that. This should be ρ0 and ρ1. This is a quantum relative entropy between the two quantum states. If you find a classical measurement that has the right probability that matches it, that should be ρ0. Then you have the optimal measurement. So basically the question we're answering quantitatively is that given the planet is there, what is the probability that you miss it? So of course there are different methods which people have studied very carefully for exoplanet detection. One of which, for example, is that you look for you wait for the planet to transit in front of the star, and you're waiting for a temporal dip in the intensity. So that's a transit method. Another one would be you look for a Doppler shift in the star spectrum in response to the planet being present. But both of those methods are more sensitive to planets which are in closer orbit. But direct imaging has traditionally been more sensitive to planets which are in further orbit for reasons which I'll go into right now. But if you want a complete survey of the exoplanet population, you really need complementary techniques. And here we're improving upon direct imaging. So now we have our two hypotheses. We can associate two density matrices associated with these two. So for the null hypothesis, you have a single spatial mode coming from the star. Or the alternative, you have something extra little coming from the planet, and we can write these down. So I'm writing this down as a cat because this mode is really spatially pure. It's not energy temporally pure, but it is spatially pure. So let's first look at the case again when we have when we receive at most a single photon at a time. Yeah, I can. Yep.
Do we really expect rho zero to be a pure state?
Yes.
Yes.
Spatially. Okay, if conditions on like, let's not go into like atmospheric turbulences and stuff, but yeah, because the star is very far away, and then by the time the star gets to where we observe, it is really a spatially pure state. It's basically it's a plane wave, and then we use a lens to focus it, and that becomes a spatially pure state.
Like, shouldn't there be all kinds of like ways and
Okay, yeah. So yes.
things that affected along the way?
Yeah.
It's like an approximation.
Ideally, we would like it to be a spatially pure state. Yeah, so adaptive optics or the wonders of instruments like PSF shaping and other stuff that astronomers can do. Ideally, so yeah, if we remove the atmosphere and everything in between, then it will be spatial.
About like cosmic dust between your star system and
yeah, let's remove that and it'll be pure. I think people can. Yeah, realistically it wouldn't be, but people are trying. So yeah. Yes. Okay. So I can go ahead and calculate the classical relative entropy for these two hypotheses for performing photon counting on the imaging, so photon intensity counting. So the measurement probabilities just looks like this. Well, basically look like that on the image stream. And the classical relative entropy for these two cases is given by S squared, so the separation squared. There's nothing you can do about that. And multiplied by epsilon squared. And epsilon, remember, is a very small number because the planet is very dim compared to the star. So my astronomer friends tells me that it is usually somewhere between a few percent to 10 to the 9. So yeah, epsilon is small. So this explains why it is so hard to see a dim object next to something that's very bright because the relative entropy is very small. So the probability that you make an error is large. Right, and now I can go ahead and calculate quantum relative entropy for these two hypotheses. And I'll just show you the plot. So the classical line as a function of epsilon, the relative intensity, is given by red here. So this is a log-log plot, so you see a difference in scaling. And so the quantum relative entropy takes up a factor of epsilon. So this is a quadratic improvement over direct imaging. And I can plot this quantity as a function of the separation. And as you see, for all separation parameters, apart from when they start being very far apart, then you do get this gap between the optimal and direct imaging. So once again, you won't believe me until I show you an ultraviolet measurement, and the measurement is the same as before. You have the centroid of your star planet system, and you just feed it into a spatial demultiplexer in the Hermit Gaussian or Hermit whatever basis you like. Basically, the fundamental mode just needs to be Gaussian. So the centroid of this thing would be given by this expression over here, where you're like most of the time you get the centroid of the star, and sometimes you get something from the planet. So the intuition is that if the planet is absent, then the centroid of the star will align with the centroid of the device, and the star is 100% coupling into the waveguide. So, and if you see anything else in the high order modes, you know that the planet is present. And my astronomer friend said, okay, you know, we can detect all well and good, but what happens to the harder problem? Because so apparently the exoplanet community is very interested in relation to detecting like signs of life. So the way they do it is to perform molecular spectroscopy. So they're looking for example, a dip for so they were looking for absorption lines where like biosignature molecules would absorb, so oxygen, methane, anything that's organic. So they were like, okay, can you do better? And it was like, okay, we can model it. So usually what they do is that they wait for the planet to transit in front of the star, and then they're looking for a difference in the star's spectrum with and without the star. Sorry, without the planet. And that problem is hard because the planet doesn't emit a lot of light. So basically we said, okay, what happens if we look at the case where you can separate the planet spatially a little bit from the star at least? So we're looking for this dip here in some bandwidth, and what we want to do with it, exactly the same as before. We take the centroid of the star planet system, we feed it into this waveguide, and we look at the spectrum of the photons that go into the high order modes. So it turns out what you can do is that for, once again, the same quantity, so for the quantum relative entropy, for missing this absorption line, we can plot the relative entropy. So kappa is like an overlap. So this is a distinguishability between the spatial overlap. Sorry, kappa is an overlap of the star and the planet's wave function. So for the transit case, with kappa equals 1, so we're all the way down here. So kappa equals 0 means that they're completely spatially separated. So once again, for all spatial separation parameters, we're seeing a big gap between direct imaging in orange and quantum in blue here. So that paper came out early this year.
I have a question about the previous slide.
Yep.
To do the measurement, it seems that you need to know epsilon.
No, we don't.
No?
We don't.
Okay.
It's basically you take a vague picture of where your star planet system is and just take the centroid. So this parameter will pop out naturally. Yeah.
Mathematically, it seems like you need to know epsilon to evaluate this, what you're saying, physical setup.
Well, I guess you take some photons to evaluate where the centroid is, but then once you kind of know where it is, and I've been told that's easy. Like apparently, like measuring centroids is always easy. You just put the centroid in each waveguide.
I was also everything here is still classical, right? I mean, when I hear like quantum, the quantum relative entropy is lower, should I basically be just thinking that that's when you're using the coherence of the?
No, sorry. When I said the quantum relative entropy, that is calculated based on the quantum state that we receive.
Yes.
Yes, but there is no coherence between the star and the planet.
Spatial coherence, right? That's what. I mean, classically, I guess you're decomposing the incident wave.
Yeah.
wave distribution along the vertical onto these different spatial modes.
That's right.
And so you're using
But these modes, like these are just your. This is a physical device that's passive, and the light here that you receive from the star and planet, that's classical and passive.
So the quantum relative entropy gives like a fundamental limit. What can be achieved in principle.
So it's not used
Using the most general thing, and then Zishin's showing the scheme that is, I guess, like pseudo-classical.
It is classical.
It is classical.
Yeah.
You can achieve
gets
that
to
limit.
that bound.
Yeah. So usually what we do is that we calculate the ultimate quantum limit, and then we find a measurement that saturates that bound.
Just so happens in this case, you're lucky, right?
Yeah.
With
Well,
the-
it's a lot. Well, we kind of basically we guessed it, but there is nothing else. Like.
Well, you could do something more exotic, but it won't do any better, right?
Yeah.
You said it's a physical device.
Yes.
I mean, can it be a simulation? Because I guess if it's a classical field I'm receiving, I could just measure not just the intensity, but the phase as well.
Yeah.
At that point, I have everything. I have all degrees
Yeah.
of freedom of the input field.
Yeah, I think
I
so.
could just simulate,
Yes.
then separate into the modes.
Yes, you can.
So I could be able to do that.
I think people have done it. So like the
It's
group.
sort of post-processing also classically that can be done.
Yes.
I don't know whether it's going to be simpler or not.
Well, there is a group at.
Go ahead.
Yeah, so there is a group at Queensland who's doing this like spatial mode sorting thing, and they're very good at it. They can sort about 200 modes with just 7 waveplates. But I guess they didn't really talk to us before, and we kind of just did it better. Yeah.
So on the previous slide, when you're talking about the spectrum analysis, do I understand correctly that, like, if you want to know the spectrum of the exoplanet versus the star, you would be looking at like the higher order terms instead of the low order ones?
Yes. So like in our model, if you are able to couple the star's light into the fundamental mode, then anything that goes into high order mode will be coming from the planet, and because you're able to separate it out optimally, maximally, that allows you to see whatever absorption feature you're looking for much more clearly. Yeah.
So actually, to come back to this question about the quantum relative entropy gives you the bound on just what one can
Correct.
expect to do. So the classical relative entropy is lower, but is there a way of stating what physics the classical relative
Oh.
like what are we not taking advantage of
Sorry,
with the
so,
CRE that makes it worse?
This one I should have specified. This is pixel by pixel spectroscopy. So you take your star and planet light, and then you're looking at and then you're doing spectroscopy on each of the pixel of your image. That makes sense.
Still be something there.
But maybe it's not so easy to articulate. I'm like what like there must be some physics that the classical relative entropy sort of it corresponds to a measurement that wouldn't be taking advantage of some
Right,
some
that's right,
physics.
yeah. So basically, this one for here, we're just not doing spatial demultiplexing. We're just not sorting out modes.
That's a direct imaging measurement.
Direct imaging, yes. So we're benchmarking against direct imaging. If the astronomers is doing something smart, they should already be not doing direct imaging,
And from direct imaging
which I think they are.
means just amplitude measurement of the
Intensity measurements on the screen. I think they are doing something smart already. But so basically my collaborator came to me and said, can you do better? I was like, what do you mean by better? And then I could tell you exactly how many photons you need to get to certain error bounds. And he said that was very useful. So yeah.
Fundamentally, we're missing the phase. If we just measure the intensity, that's the physical degree of freedom.
I believe there is something called the stellar coronagraph, which is doing something abstractly similar to what we're proposing.
Oh, sorry, I had a question. So for the quantum relative entropy, if the input is classical, wouldn't it just be equal to the classical relative entropy?
Oh, so the classical relative entropy assumes a measurement, but the quantum one does not. So the quantum one is your ultimate limit, and you need to find the correct measurement that will.
So would it be equal to there's a quantity called the measured quantum relative entropy? Would that be equal?
It's not. The measured relative entropy involves an optimization of our old single mode measurements. That's where this classical one is assuming a particular direct energy measurement.
So is it just if you know the optimal measurement, you can saturate this bound classically?
It's not necessarily the case that the optimal single mode measurement is the optimal collective measurement.
Okay.
Yeah, so I've been told by our mutual mentor, John Dowling, that if you want to work with experimentalists, then you need to work with almost exactly what they have, and otherwise they'll tell you to go away. So, so we'd like to work with experimentalists. Turned out that implementing this spatial multi-multiplexing is non-trivial. And we thought, what can we do given that we have these nice people to collaborate with? So it turns out that you can just replace the lens with two collectors. So this is basically sacrificing intensity for, well, the experimental scheme being simple, but this kind of experimental scheme is actually pretty, well, I want to say exactly analogous to what they do in stellar interferometers. So we're not that far from reality. So what you do is that you replace a single lens here with just two collectors. You take what you have, you apply a phase shift, you put it through a 50-50 beam splitter, and then you do photon counting at the end. So I can calculate the quantum state that's collected at these two sites. So I'm calling it star and planet. And I can calculate the quantum relative entropy for the state. Turned out that it has the correct linear scaling in epsilon that we want. So we're like, okay, great, let's work with that. So we implemented this. So the experimentalists among you might understand this better than me. So it turned out it's not so easy to get a thermal source in the lab. So we turned the laser into a thermal source, which is quite bright. So yeah, we put it through a phase modulator and amplitude modulator, and then we put it through some multimode fibers. It sprays out into this lens that collimates it, and then we fabricated some masks. I think they are silicon on gold that simulated our planet and star. It sprays out into free space, so there's a meter between our mask and our collectors. So these are actually just fiber tips. Ideally, we'd like to use something that's a bit bigger in aperture, but we have fiber tips. We have an air gap that we can adjust, which means that we can apply different phases that we need. And then there's a 50-50 beam splitter and a photon counter at the end. So we did this experiment. This is what our chip looks like. And so that's that part. And then we can measure experimentally the relative, okay, we can measure the probability distributions, and then we can turn that into a relative entropy plot. So what we're doing here is that as a function of epsilon, so the intensity of the planets, which we can adjust, direct imaging is given by this teal dashed line down on the bottom. The blue is the ultimate quantum limit. And so our experimental data points are in red. So we were quite surprised to see that for epsilon equals to 10 to the minus 3, so this is every 1,000 photons, we see one coming from the planet. We're doing 2 orders of magnitude better than direct imaging. with a lens compared to a lens of the same diameter. So yeah, we're pretty happy because we have an interferometer that has like 99.5% visibility. And then we can go ahead and measure, if the intensities are equal, we can go ahead and measure the separation between those two sources. So on this plot, we are showing a mean square error here. So we want a small mean square error because that's small errors means it's good. So the ultimate quantum limit is equal to 1 on this plot, and it's this blue line down at the bottom. The green teal is direct imaging. So what we're claiming here is that for two sources which are separated by 15 microns at a meter away, we managed to resolve those to about 1.7% accuracy. So that's this data point over here, which is about 2 to 3 orders of magnitude better than direct imaging. Yeah, so that was good. So in conclusions for this part of the work, okay, nothing is quantum, everything's classical. We are able to do sub-Rayleigh quantum state discrimination for exoplanet detection, and we measure the separation of those two sources to a couple of orders of magnitude better than direct imaging. Are there any further questions on that part? Okay. I should try to talk about this next part quickly. Okay, so now that you know what classical measurements do, I'll tell you about how we can enlarge the baselines. So sure, we can do all these super resolution tricks, but then the resolution of these tricks are still proportional to the baseline of our imaging aperture and the wavelength. So ideally, we like to use as large a baseline as possible. So yeah, so imaging requires measuring both amplitude and phase information from our incoming state. Currently, we can do that in microwave and radio because we can measure the oscillation of the electric field directly. But we can't do that in optics because there is just no state-of-the-art electronic fast enough to follow the oscillation of the electric field. But if we were able to move into the optical, then we gain a factor of the we gain a factor between 10 to the 3 and 10 to the minus 10 to the 5 in resolution, and we like that. So let's imagine. So yeah, so the motivation was that, you know, imagine seeing this picture except 10 times, well, no, 10,000 times sharper. And then we like to mitigate noise and transmission losses in the middle. So there are a few approaches that have been designed before. So there has been the Goddardson scheme, which looked at sending single photons into a beam splitter and then distribute that to the different telescope sites. So the problem there is that you want single photons which are phase stabilized, and we don't even know in principle how you would distill single photon Bell states. And then the Harvard group derived a very efficient encoding scheme for multiplexing frequency and time bins. But I think their scheme suffers from multi-photon events, as well as they don't have a way to robustly encode the starlight information. So here we say that we have a framework for encoding the starlight into the quantum error correction state.
Say Harvard group, do you mean Lucan?
I think we cited them at some point. And then I think he's kind of pissed. I hope he doesn't get pissed off at me. Okay.
I didn't hear that part.
So here's our protocol. We have Alice and Bob holding 2 telescope sites each. These are spatially separated because we want a large baseline. We collect light into these 2 sites, and we want to absorb the light into quantum memories. So that's just this part over here. And then we want to encode it onto a quantum error correction code that can protect information for when we measure it. So that's the encoder, and that's noise channel that acts onto the memory states. Here is a slightly more blown up version of the encoder. So we will use STIRAP, stimulated adiabatic quantum passage, to encode the state, and then we can post-process it later.
Where is the noise in the blown up diagram?
That happens afterwards.
Or PA?
Before PA, after PA, this is a, yeah. Oh, I guess it happens, yeah, afterwards. So we're looking at the error on the quantum memories. We haven't quite gone to fault tolerance yet. Yeah, and then afterwards, you can choose your favorite quantum error correction code to measure the state. I'll speed up a little bit, a bit more over here. So in the weak photon limit, so once again, we're receiving a single photon at a time between Alice and Bob. Most of the time, we just get vacuum. Sometimes we get a single photon, and then there's a phase phi in the middle that we want to measure. And sometimes we get a plus state, and sometimes we get a minus state, depending on the spatial distribution of the source. So we're interested in measuring both gamma and phi, because gamma is related to the spatial distribution of our source, how wide it is, and phi, which is related to the location of the source. So this is our encoder. Feel free to fall asleep if you're not interested in atomics. So what we do here, we have our cavity where the photon is in. We use 3 systems. The register, which contains our logical 0 and 1 state. So this is the code that we want to imprint on. We have the ancilla atom 1, which is green, and ancilla atom 2, which is red. So for atom 2, there are 3 different levels. So there's the excited state, 1 and 0. We can tune the interaction between 1 and the excited state. So for example, this could be via the strength of a laser or the polarization of a laser. And the 0 state, the interaction between it and the cavity is fixed by this parameter G here, and it's dependent on the properties of the cavity. And in the rotating wave approximation, the Hamiltonian for the ancillary atom 2 looks something like this. So the only thing I want to point out is that one of the 0 energy eigenstates of this Hamiltonian looks like this, where it's coupling the photon state. So the photon state, n is the number of photons in the cavity, and these 2 levels. And if we have omega t much, much larger than g at the beginning, then the 0 is approximately the ground state. And if we can tune down omega adiabatically such that at the end of the interaction, such that omega g is much larger, then we've transferred the quantum information from the starlight into the 0 level. And so that's what we do here. So we go from the 1 level to the 0 level with a pulse that looks something like this. So what we do is that we prepare the register and the green ancillary atom in initial Bell state to begin with. If there's a starlight photon in the cavity, then the atomic level will shift from 0 to 1. So, and then we do a Bell measurement between the green and the red to teleport the state of the starlight onto the register. So that is just to say that after all that step, you have the starlight photons information imprinted onto the quantum error correction code, and now that's protected from your choice of noise. And yeah, I won't talk about this, but let's compare the performance of our scheme with and without quantum error correction. So without quantum error correction, the quantum Fisher information for the parameter phi follows this red curve over here. And even if you just use a simple repetition code with 3 or 4 qubits, then you get a huge gap. And as you increase the number of qubits in the memory state, this will become a top hat function, and you can basically tolerate as much dephasing as you want.
What kind of noise are you assuming here?
So this we're assuming a dephasing noise channel. This is depolarizing. Yeah, so
this is a repetition code to protect against dephasing.
Yes. Yeah. So yeah, so even if you use a simple code, you get a big advantage. And we can also look at the limit of large quantum codes. So don't ask me anything to do with his part because that's Xingkai's work. So he figured out that even if you look at almost adversarial noise, our scheme, if you use a nice code such as a random quantum code, you can tolerate up to about 10% error on the qubits while still preserving the quantum field information, and that's much less stringent compared to universal quantum computing. Yeah, so if you have pure dephasing, we can tolerate up to almost like entirely dephasing channel. So thank you for my funding agencies for funding this work. We have collaborations currently active at various universities. We are open to further collaborations.
Oh,
Yeah.
I'm just saying hi, I'm at Cornell.
Oh, oh yeah, sorry. This was done before.
Sure.
The slides were done 3 months ago. Sorry. Yeah, we have PhD scholarships available from the City Quantum Academy. Here's the team, and thank you for your attention.
Nice discussion during the seminar. Any further questions? Clarification?
Out of curiosity, for the second part of your talk, which is, I think, very exciting, how far we are from making that practical in terms of years?
Depends on, so basically we will need pre-distributed entanglements stored in quantum memories waiting at 2 sites for it to happen. I believe maybe just a couple of months ago, the Australian government did one of these feasibility study quantum technology projection report thingies, and they said we're going to have quantum computers before we have the quantum internet, and this is a very nice application of the quantum internet. But I guess for short-term stuff,
But this doesn't require, for the quantum error correction code, that requires quantum computation. You're saying that part requires quantum computation also? It seems simpler.
It is much simpler, but we need pre-distributed entanglement in fault-tolerant memories at different sites. So, and I keep hearing noises on how we have a few hundred qubits now locally, but we don't have a few hundred qubits.
Oh, no.
Yeah, so get your experimental partners working very hard, and we might have.
So it's kind of beautiful to imagine cavity QED also with starlight. But that also sounds quite hard, and it sounds like one of the other challenging aspects because you're dealing with also usually fairly broadband light from stars, right? So
that's right.
So you frequency filtering those pretty heavily.
Yes, you can frequency demultiplex and then time demultiplex. Those two are basically the same thing, right? So the Harvard group
Have a bunch of different cavities and atoms in them for each.
We're currently working on schemes which will hopefully work with what frequency, but that's work in progress.
Okay. Do you know of any experiments that are trying to do some sort of with starlight and cavities?
I do have a collaborator who wants to try the classical, the first part of the talk on 2 telescope sites, but with the quantum stuff, apparently even step 1, nothing quantum, trying to couple starlight into a cavity, that's in itself pretty hard. Yeah, and whenever I talk to my astronomy friends, they're like, this is science fiction, we'll come back. When you have something in 20 years, come back, but I don't care about something in 20 years. Yeah.
What happened to your hamster in the UK now that you're in Australia?
The hamster lived out its full life. She lived about 3 years and passed away a week before I left for Australia.
Oh, sorry about that.
But she outlived her expected life expectancy by about 50%. So.
All right. Any other questions? Let's thank Zishen. I told you about current. My mental is not.
Oh, sorry, car.
Current.
Talk.
Yeah, Francesco. Yeah. Here is the blinded by the light.
So I was kind of amused that people told you that the spatial mode demultiplexer is very non-trivial. Like for in waveguides or I mean if you try to do it in optical fiber, I think it's quite hard. But if you
I know that there are companies which sell these now, but
yeah.
at the time the paper was written about 2 years ago, it was not trivial. And then the Queensland group just told me
Right,
about
but
2 months ago that they have
you have
eyes.
And they can demultiplex, right?
Yeah.
But we have to experience data. Hard, but maybe more in one dimension. You have many multiple modes like along one dimension. And you multiplex it without control.
Okay. Nobody's I've seen has implemented in the waveguides yet.
Okay.
Because I'm just talking to the wrong crowd.
Okay, I think I could send you a couple of, there was one kind of a nice paper, very similar to the kind of geometry shown in cartoon, right? But the group that you say has 200 modes. They have designs for these multiplexers or
They're not working with waveguides. They're just working with waveplanes. But they managed
it's already long.
more than 20 modes with 7 waveplanes.
Oh,
Face to face.
All right, I'm sure your email is on yeah, I'll send you a reference or two because I think it's there. Yes. Definitely with waveguides, it's doable. With
Or more like I think
but you don't even need that many modes, right? I mean, for the kind of discrimination of 2 things that you wanted. I mean, I would think the first 3 or 4 modes give you most of the information.
Yeah, it depends on how far away they are. Basically, if they're far enough that you need the higher order modes, then you don't need that anymore because the classical thing is pretty optimal. But then, yeah, if they're very close, then you don't need a couple.
Yeah, but also, I'm still wondering, can you do that on a computer with simulation? You record your amplitude and then.
What do you mean by? So you mean just direct imaging, but then just some sort of signal processing after that?
Just like people do phasor retrieval, for example. There
Yeah,
are
I also
phasor retrieval.
it's a signal to noise. I think of it as a signal to noise ratio. Somehow you're saying like with some given noise on each detector.
People in microscopy have been doing this for a long time to go a little bit beyond what they could do with a direct imaging system. They have all sorts of phasor retrieval algorithm and things like that. So I wonder if you record that and then you do post-processing, a way to do that.
Record the amplitude and phase information from. So we think about a lens and the whole thing.
You could have like if you need the phase, you could do it.
Okay, I think so. Yeah, maybe.
Yeah.
I don't know very much about.
Also wavefront detectors. I don't know if they are. Maybe it's actually simpler to do it experimentally than introducing numerical errors in post-processing. I don't know which one would be best. But yeah, since there is nothing really quantum in your physical detection system.
Yeah, correct.
I guess one in theory could do it with post-processing. But yeah, I'm not sure.
But is the light is your measurement device sensitive to single photons?
So you do need single photon detection.
Well, if your light is very weak.
So maybe that's the point. So
I think the argument as to what you gain by separating these modes versus not, I think that's more fundamental than whether you're dealing with the higher or low light level, right? I think it applies even if your light level is high.
But if you are directly imaging with few photons, are you losing something when you are detecting at that point? Instead of detecting after you have separated all of the modes physically? I think
probably not.
Detection.
I agree. I think like either way, your signal has just gone down, right? So your signal in either in